Topic 17A, Rates of Chemical Reactions. Up to this point in the course, we've really been talking about processes in thermodynamic terms, and we've been using them to predict whether or not things will occur spontaneously. And so we could extend that to any kind of process, for example, spontaneous human combustion. We can apply a thermodynamic argument if we approximate spontaneous combustion just in terms of the glucose that makes up some of our bodies. So according to thermodynamics, if we write out the balanced chemical equation, then we can calculate the Gibbs free energy for the constant pressure, constant temperature process for this chemical reaction, and that should predict whether or not we will have a spontaneous process. The Gibbs energy for this reaction turns out to be a very large negative number, which actually suggests that it is a spontaneous process, and so spontaneous combustion may be a real thing. However, what we are missing from the thermodynamic treatment is information about time scale. So I don't know how much time it will take for the spontaneous reaction to happen. We need more information about the reaction rate. A kinetic experiment is an experiment that tells us how fast the reaction goes. We can do this by monitoring the concentration of a substance, for example J, as a function of time in a chemical reaction. For example, if J happens to be a reactant and we can plot its concentration as a function of time, we should see a decrease in that concentration and use the slope of the tangent to the curve to give us a measure of the rate of the disappearance of that reactant with the subscript of J. And this is equal to the change in the concentration of J divided by the change in time. There's a negative sign in front of that to give us a positive rate, so that's the rate of disappearance for my reactant J. On the other hand, if J happens to be a product, then we can measure its concentration and see an increase as the reaction progresses. Again, the slope of the tangent to the curve will give us the rate of the appearance of that product, J. We want to talk about rates of reactions rather than rates of disappearance of reactants or appearances of product, even though these are the things that we measure. So we've measured, for example, the rate of the consumption of A, and we can talk about that in terms of the slope of the tangent to the curve. And we know that if we lose A, we will produce B at twice the rate because we're producing 2 equivalents of B for every equivalent of A that we have. So we would have to adjust for the rate of the appearance of B with this factor of 1/2. And that 1/2 accounts for the fact that we are producing 2 equivalents of B for every single equivalent of A that is consumed. We want to be able to talk about reaction rates in more general terms. So instead of rate of consumption of A or rate of production of B, we want to talk about a reaction rate. So a reaction rate, we give that the symbol epsilon. Now it has no subscript because it indicates it's the general rate for the reaction. And the general equation for this rate is given here, where we have this extra factor of 1/V sub x. Now this happens to represent the stoichiometric coefficient in the balanced chemical equation for that reactant. And we're following the same convention that we've done in the past, where that stoichiometric coefficient is negative if we are dealing with a reactant, or positive if our substance X happens to be a product. And so this gives us a general way to describe the rate of a reaction in terms of either a reactant or a product concentration. One of the things you may have noticed in the rate measurements is that the rate does depend on the time in which we make the measurement. And it would be more convenient to talk about rates without having to indicate what time we made the measurement. This is done using rate equations known as rate laws. And these rate laws relate rates and concentrations using rate constants. So take this generic example of a reaction A plus B producing C. So the rate of the reaction, according to the rate law, would depend on the concentration of reagent A and the concentration of reagent B. They're related to the reaction rate by this constant K, which we call the rate constant. The dependence of the rate on reagent concentrations also depends on these exponents, A and B, which are called reaction orders. And reaction orders, as well as rate constants, both must be determined by doing experiments. So a reaction order sometimes is related to the stoichiometry of the balanced chemical equation. And as an example of this, we can look at the radioactive decay of carbon-14 to produce nitrogen-14. And the rate at which this occurs depends on the concentration of the carbon isotope to the power of 1. So this would be a first-order reaction with respect to the C14. This is a case where the reaction order equals the reaction stoichiometry. However, there are also examples where the reaction order does not equal the reaction stoichiometry. So for example, NO2 combining with carbon monoxide to form NO and carbon dioxide. The rate law for this equation depends on the concentration only of the NO2, and it has a reaction order of 2 with respect to this reagent. So even though there's no stoichiometric coefficient of 2 in front of NO2 in the balanced chemical equation, the reaction order has experimentally been determined to be 2. Another example of this is the hydrolysis of a methyl acetate. This is a reaction that can be catalyzed by a number of different species, for example, imidazole. And in the presence of imidazole, the rate of this equation can be described using the concentration of methyl acetate as well as the concentration of imidazole. Imidazole is a catalyst and actually isn't consumed in the reaction. It just makes it go faster. We can say that this reaction is a first order in methyl acetate and first order in imidazole, even though imidazole is not in the balanced chemical equation. Overall, we would call this a second-order reaction. We can determine the overall reaction order taking the sum of the reaction orders for each of the reagents. So how do we find the rate law? If we have a reaction involving just a single reactant, then we can follow this method. First, we would measure the rate of the reaction using a known concentration of our reagent A. We would repeat this experiment with another concentration of A, maybe 3, 4, 5 times. We take those rate measurements and we plot the log of the rate versus the log of the concentration of A. And we could get something that looks like this. So we have the log of A on the x-axis, the log of the rate on the y-axis. And what we should get is a straight line where the slope would be equal to the order of that reaction. If there are only 2 points available, in other words, we've only measured the rate for 2 different concentrations of A, then instead of using this graphical method, we can do the calculation using the log method. So we only have 2 points available. Then we take the ratio of my rate measurements, so rate of the reaction under experiment 1 with the concentration of A in experiment 1, and then the rate of experiment 2, which was obtained with a concentration of A in experiment 2. We can recognize that the rate constants being the same will cancel out, and then we can take that exponent of A, which remembers our reaction order, and make it an exponent for this ratio of concentrations. Now at this point, if we take the log of both sides, this makes it a little bit easier for us to isolate for the reaction order A. So one of the properties of the log of an exponent is that we can take that exponent and put it in front of the log so that it becomes A times log concentration of A in experiment 2 divided by concentration of A in experiment 1. Now this is just a simple rearrangement to solve for the reaction order, where A, the reaction order, is equal to the log of the ratio of my rates divided by the log of the ratio of the concentrations. This log method for calculating the order of a reaction is usually combined with the method of initial rates, where the rate is measured at the beginning of the reaction. So for example, if we're measuring the rate of a reaction by monitoring the appearance of the product over time, then we can take the slope of the tangent to the curve at the very beginning of the reaction. This gives the initial rate, where we are indicating that the measurement is done at time t equals 0 with this not subscript. By measuring the rate at the beginning of the reaction, we can make the following assumptions: that the concentration of A during the measurement is more or less the same as the concentration of A that we started out with, and this is a known quantity. In addition, because we're just measuring the initial part of the reaction, we can make the assumption that the concentration of A hasn't changed very much, and so it is a constant. If we were to apply this approximation to our log method, then now the reaction order is given by this equation, which is the same as the equation on the previous slide, except now we're talking about initial rates and initial concentrations. If we have more than one reactant, we can use the log method to find the reaction order for each of our reagents. For example, suppose I have 2 reactants, A and B, that gives rise to some product. I know the rate equation under initial conditions will be equal to the rate constant times the initial concentration of A to the power of its reaction order multiplied by the initial concentration of B to the power of its reaction order. If we perform two rate measurements with different concentrations of A and the same amount of B, we can apply the log method. This would be in the presence of a fixed amount of reagent B. Now the equation, which is the ratio of my rates for experiment 2 over experiment 1, would be equal to the ratio of the rate laws for this reaction under these two different conditions. Now, because B is the same concentration and the rate constants are the same, these will cancel out, which means that my two rate measurements can be used in the log method to find the reaction order A. We take the ratio of the concentrations to the power of the reaction order A, and then we solve for A. And this would be the reaction order for this reaction with respect to A. Then we simply repeat the series of measurements, but this time we hold the reagent A constant and change the concentration of reactant B. So now we can cancel out the concentration of A as well as the rate constants in this ratio. And now, using the same mathematical manipulations, we can solve for the reaction order of B. Once we know the reaction orders for each of the reagents, we can use the rate equation along with the values for one of the experiments that was performed to solve for the rate constant. So the rate equation, in this case, again, it depends on the rate constant as well as the concentrations of my two reagents to the power of the reaction orders. We rearrange to solve for K. We can take a rate measurement for one experiment where we now know what the reaction orders are for reagent A and reagent B, along with the concentration of the two reagents used to find out what that value would be for the rate constant. So in this video, we have looked at definitions for reaction rates using the general equation. We've also learned how to find order of reaction given a series of rate measurements at different concentrations. And so this involved the use of the log method, the method of initial rates. And if we have more than one reactant, then we can use the isolation method. This allows us to get more information about the rates of reactions, such as the multitude of reactions that occurs in biological systems, where we have a complex soup of enzymes, small molecules, and other proteins working together to sustain life.